Every photograph of the universe is lying to you. Those Hubble and Webb images showing galaxies scattered across the cosmos like glitter on black velvet. They make it look like the universe is full, crowded, busy. It is not. The space between galaxies is not just empty. It is a category of emptiness so extreme that nothing in your everyday experience can prepare you for it. Interstellar space, the void between stars, is already terrifying. But intergalactic space makes interstellar space look like a packed stadium. Out there between the galaxies, you could travel for millions of years at the speed of light and encounter almost nothing. No stars, no planets, no dust. Just a near-perfect vacuum stretching in every direction, forever. If this is the kind of deep space exploration that grabs your attention, consider hitting the like and subscribe button. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. Look at any photograph of the deep universe and tell me what you see. Galaxies. Hundreds of them. Thousands. Bright spirals, golden ellipticals, faint blue smudges piled on top of each other in every direction. The Hubble Ultra Deep Field alone captured roughly 10,000 galaxies in a patch of sky smaller than a grain of sand held at arm's length. The James Webb Space Telescope pushed even deeper and found more. Everywhere the cameras pointed, galaxies appeared. Packed together, overlapping, filling the frame from corner to corner. That image is one of the most beautiful things science has ever produced. It is also one of the most misleading. Because what those photographs do not show you, what they physically cannot show you, is the distance between those objects. Every deep field image compresses billions of light years of depth into a flat rectangle on your screen. Galaxies that are hundreds of millions of light years apart appear to be neighbors. Objects separated by gulfs of emptiness so extreme that nothing meaningful exists between them look like they are practically touching. Imagine standing on the roof of a tall building in a dense city at night. You see lights in every direction, buildings, streets, cars, windows glowing for miles. The world looks full. Now imagine someone told you that everything you were seeing is real, but the distances between those lights have been compressed by a factor of 1,000,000. The nearest building is not across the street, it is on another continent, and between you and it, there is nothing. No ground, no air, no structure of any kind, just emptiness, stretching so far that the light from that building took years to reach your eyes. That is what a deep field image does to the universe. It takes a cosmos that is overwhelmingly, staggeringly, almost perfectly empty and makes it look full. And the consequence of that illusion is that most people dramatically underestimate the true nature of the space between galaxies. They think of intergalactic distance as a bigger version of the distance between stars. It is not. It is not even in the same category. And understanding why requires starting with something closer to home. It requires starting inside our own galaxy and understanding what emptiness means before you ever try to leave. The Milky Way is roughly 100,000 light years across. That number sounds large, and it is, but it is not the number that matters. What matters is what is inside that span. Our galaxy contains somewhere between 100 billion and 400 billion stars. That is an almost incomprehensible quantity. If you counted one star per second, 24 hours a day, with no breaks, it would take you more than 3,000 years to reach 100 billion. And depending on the true count, you might need to keep going for 10,000 more. With that many stars crammed into a disk 100,000 light years wide, you might expect the inside of a galaxy to be a busy, crowded place. A place where stars are stacked close together, where light fills every corner, where the sky is brilliant in every direction. It is not. The inside of a galaxy is shockingly, absurdly empty. Here's the fact that changes everything. The nearest star to our Sun is Proxima Centauri. It sits approximately 4.25 light years away. 1 light year is roughly 5.88 trillion miles. Multiply that by 4.25, and you get a distance of about 25 trillion miles between our Sun and the closest other star. 25 trillion miles of almost nothing. To feel what that means, shrink the Sun down to the size of a basketball. At this scale, the Earth would be a tiny bead about the size of a peppercorn, sitting roughly 28 yards from the basketball. That is already a startlingly large amount of empty space for a solar system that feels so compact in diagrams. But Proxima Centauri, at this same scale, would be another ball, smaller than the basketball, sitting approximately 4,300 miles away. That is roughly the distance from New York to Berlin. 1 basketball in New York, 1 in Berlin, and between them, nothing. No other basketballs, no peppercorns, no matter of any significance at all. Just 4,300 miles of open space containing almost zero objects. Now multiply that by hundreds of billions of stars, and you start to understand what a galaxy actually is from the inside. It is not a glowing fog. It is not a dense cluster of lights. It is a vast, empty arena in which tiny points of light are scattered so far apart that the distance between any two of them dwarfs the objects themselves by a factor of millions. If you were placed randomly somewhere inside the Milky Way, the odds are overwhelming that the nearest star to you would be light years away, and the space between you and it would contain almost nothing detectable. That almost nothing deserves its own explanation, because it reveals just how empty even the inside of a galaxy really is. The space between stars is called the interstellar medium. It is not a perfect vacuum. It contains gas and dust, primarily hydrogen, along with trace amounts of helium and heavier elements. But the density of this material is so low that by any human standard it qualifies as emptiness. In the general regions of our galaxy between the spiral arms, the interstellar medium contains roughly 1 atom per cubic centimeter. 1. A single hydrogen atom floating alone in a box the size of a sugar cube. For context, the air you are breathing right now contains roughly 25 quintillion molecules per cubic centimeter. That is a 2 followed by 19 zeros. The interstellar medium is approximately 25 quintillion times less dense than the air in your living room. If you built the most powerful vacuum chamber in the world, pumped out every molecule you possibly could, and measured what was left, you would still have a medium that is trillions of times denser than the void between the stars. Interstellar space is so empty that a spaceship traveling through it at tremendous speed would encounter almost no resistance. There is no friction to speak of, no drag, just an occasional atom bumping into the hull once every fraction of a second, depending on speed and direction. The emptiness between stars is so complete that even light, which fills the galaxy in every direction, does so only because photons from billions of sources add up over enormous distances. At any individual point between the stars, you are in darkness, surrounded by cold, silent near-nothingness, with the nearest star a shimmer so far away It is just another dot among millions. And here is the part that most people never stop to consider. That interstellar medium, that astonishing emptiness averaging 1 atom per cubic centimeter, is the crowded version. That is the space inside a galaxy where things are close together, where there are stars and gas clouds and dust lanes and molecular nurseries. The inside of a galaxy is the populated zone, the neighborhood, the city. Now look outward. Reach the edge of the Milky Way. Cross the boundary where the stars thin out and the last faint halo stars flicker against the black, and stare into the space between galaxies. What you are looking at is not just more emptiness. It is not a wider version of the interstellar vacuum. It is something so much more desolate that the transition between them is like stepping from a dense forest into the open ocean and realizing the ocean goes on for 1,000,000 miles with no land in sight. That transition from galaxy to void deserves a closer look, because it is not a clean line. You do not walk through a door and suddenly find yourself in intergalactic space. The edge of a galaxy is a gradient, a slow thinning, a fade that stretches across hundreds of thousands of light years. And understanding what that gradient contains and where it finally ends is essential to grasping what comes after. The visible disk of the Milky Way, the part you see in photographs, is roughly 100,000 light years across and about 1,000 light years thick. That disk contains the spiral arms, the dense star-forming regions, the molecular clouds, the bulk of the stellar population. It is what most people picture when they imagine a galaxy. But the disk is not the whole galaxy. It is not even close. Surrounding the disk is a structure called the galactic halo. The halo is a roughly spherical region that extends far above and below the plane of the disk, reaching outward to perhaps 130,000 light years from the galactic center or more. It contains old stars, mostly dim red dwarfs and ancient stellar remnants, scattered thinly through an enormous volume. It also contains globular clusters, dense balls of hundreds of thousands of stars that orbit the galactic center on long, looping paths that carry them far from the disk. The halo is real. It is part of the Milky Way, but it is dramatically emptier than the disk. The stars in it are separated by distances far greater than the average spacing inside the spiral arms. If the disk is a city, the halo is the rural countryside surrounding it, sparsely populated, quiet, and growing emptier the farther you travel from the center. The sky seen from inside the galactic halo would still show stars, but fewer of them, dimmer, and more widely scattered. The brilliant band of the Milky Way would still be visible behind you, but you would already feel the thinning. The galaxy would be loosening its grip. Beyond the halo, there is one more layer, one more zone of fading influence before the void truly begins. Scientists call it the circumgalactic medium. It is a vast envelope of diffuse gas, mostly ionized hydrogen and heavier elements, that surrounds the Milky Way and extends outward to at least 300,000 light years from the galactic center, with more recent studies suggesting it reaches 600,000 light years or more, roughly to the edge of the galaxy's dark matter halo. It is not visible to the naked eye. It does not glow in any wavelength you could casually detect. Its existence was confirmed through painstaking observations of distant quasars, the brilliant cores of far-off galaxies whose light passes through the circumgalactic medium on its way to our telescopes. When that light arrives, it carries absorption signatures, specific wavelengths dimmed by the gas it passed through, And from those signatures, astronomers have mapped the extent and density of this envelope. The circumgalactic medium is thinner than the interstellar medium inside the disk, but it is denser than the true intergalactic medium beyond it. It occupies a middle ground, a transitional zone where the galaxy's influence is still detectable but fading. It contains gas that has been expelled from the disk by supernova explosions and stellar winds, material that was blown outward and now hangs in a diffuse cloud around the galaxy. Some of that gas will eventually fall back inward, recycled into new generations of stars. Some of it will drift outward and merge with the intergalactic medium, lost to the galaxy forever. This is the last zone of belonging. The circumgalactic medium is the outermost boundary of what can meaningfully be called the Milky Way's territory. Beyond it, the gas density drops again, steeply, and the material you encounter is no longer associated with any galaxy. It is the intergalactic medium, the void, the true between. Think of it as a shoreline. The disk of the galaxy is the dry land, dense and populated. The halo is the beach, sloping downward, the ground softening beneath your feet. The circumgalactic medium is the shallow water near the shore, still connected to the land, still influenced by it, but already part of something larger. And beyond the shallows, the continental shelf drops away. The ocean floor plunges to abyssal depths. The water temperature changes, the light from above fades to nothing, and you are in the deep ocean, thousands of meters of featureless water beneath you and nothing but open sea to every horizon. That drop, that transition from the circumgalactic medium to the intergalactic void, is where the emptiness changes character. Inside the circumgalactic medium, you are still within range of a galaxy's gravitational and chemical influence. Gas cycles in and out. Material has a history and a destination. The medium is thin, but it is connected to something. Beyond it, that connection ends. The gas you encounter belongs to no galaxy. It has no cycle. It is not going anywhere. It simply exists at a density of roughly 1 particle per cubic meter, stretching in every direction for millions of light years until the circumgalactic medium of the next galaxy begins to thicken around you, signaling that another island is finally, after an unimaginable crossing, within reach. The Milky Way has a boundary. It is not sharp. It is not marked, but it is real. And once you cross it, you are no longer inside anything. You are between. And the between is where most of the universe lives. But before we cross that boundary, there is something else the photographs hide. Something about the way galaxies actually appear from up close that shatters another common misconception. When you see a galaxy in a photograph, it glows. It has visible structure, spiral arms, bright cores, lanes of dark dust silhouetted against stellar light. The image communicates density, solidity, mass. You look at a spiral galaxy and your brain interprets it as a thing, a coherent physical object, a bright wheel of material spinning in space. And it is a coherent object held together by gravity. But the photograph lies about how much of that object is actually stuff. The overwhelming majority of a galaxy's volume is empty space. Stars occupy a vanishingly small percentage of the total volume. If you removed every star, every planet, every speck of dust, and every atom of gas from the Milky Way, but left the gravitational structure intact, the galaxy would look almost exactly the same from the outside, because the dark matter halo that surrounds it accounts for roughly 90% of its total mass and extends far beyond the visible disk. The luminous part, the part you see in photographs, is a thin, bright film stretched across a vast, dark scaffold. This matters because it changes how you should think about everything that comes next. When we talk about the distance between galaxies, we are not talking about the distance between two solid objects. We are talking about the distance between two enormous regions of mostly empty space, and the gap between those two regions is even emptier. Think of it this way. You live on a planet. That planet orbits a star. That star is surrounded by light years of near vacuum, populated only by a few stray atoms per cubic centimeter. That star exists inside a galaxy that is 100,000 light years across, but is overwhelmingly empty space. And that galaxy, that vast, diffuse, mostly empty structure, is itself just one island in a cosmos where the space between the islands is orders of magnitude emptier than the space inside them. Each level of the hierarchy is emptier than the last, and each transition between levels is not gradual. It is a cliff. The density does not taper off gently as you leave a galaxy. It drops steeply. The interstellar medium gives way to the intergalactic medium, and when it does, the emptiness you encounter is so extreme that the interstellar vacuum, that terrifying 1 atom per cubic centimeter void, begins to feel populated by comparison. This cascading emptiness is the feature of the universe that photographs erase. Every image of a galaxy cluster, every map of large-scale structure, every artist's rendering of the cosmic web compresses the voids and highlights the nodes. The bright parts get shown, the empty parts get cropped, and the viewer walks away with the impression that the universe is a richly textured fabric, where galaxies are strung close together like beads on a string. They are not. The beads are real, the strings are real, in a sense, but the space between the strings is the dominant feature, not the strings themselves. The universe is not a web with some gaps. It is gaps with a thin web stretched across them. And understanding that inversion, truly feeling it rather than just hearing it, is what separates a casual glance at the night sky from a genuine reckoning with what the cosmos actually is. There is one more thing the images fail to communicate, and it is perhaps the most important failure of all. Scale. When you look at a deep field image, the galaxies come in different sizes. Some are large, bright spirals, some are faint red dots. Your brain automatically interprets the large ones as being close and the small ones as being far away. And in some cases, that is correct. But in many cases, the size difference has nothing to do with distance. Some galaxies are physically enormous, some are tiny dwarfs, some are bright because they are forming stars at a furious rate. Some are dim because they stopped forming stars billions of years ago. The result is that you cannot look at a deep field image and extract any meaningful information about the actual spatial arrangement of the objects in it. Two galaxies that appear side by side on the image might be separated by hundreds of millions of light years. Two galaxies on opposite corners of the frame might actually be relatively close in three-dimensional space. The image is a projection, a flat shadow of a three-dimensional reality. And that shadow erases exactly the information you need most: the distances. This would be merely an aesthetic problem if it did not have a deeper consequence. The consequence is that for most people, the mental image of the universe is fundamentally wrong. They picture galaxies distributed in space the way stars are distributed in a galaxy, as points of light scattered at modest intervals through a vast but navigable volume. In this mental image, traveling from one galaxy to another would be hard, certainly. but it would be a matter of crossing a distance. You leave your galaxy, you fly through empty space for a while, and eventually the next galaxy appears on the horizon, growing larger and brighter as you approach. That is not what would happen. What would happen is this. You leave the Milky Way. The stars thin out. The last faint dwarf stars in the galactic halo fall behind you. And then you enter a darkness that does not end, not for millions of light years. The nearest major galaxy, Andromeda, is 2.5 million light years away. At the speed of light itself, the fastest speed permitted by the laws of physics, that crossing would take 2.5 million years. And during every second of those 2.5 million years, you would see almost nothing. No stars ahead, no stars behind, eventually, as even the Milky Way fades to a faint smudge and then disappears. No planets, no asteroids, no comets, no dust clouds, nothing to bounce a signal off of, nothing to navigate by. Just a thin, hot, almost invisible plasma of ionized hydrogen, stretching in every direction at a density so low it barely qualifies as matter. The interstellar medium has roughly 1 atom per cubic centimeter. The intergalactic medium, the material between galaxies, has roughly 1 atom per cubic meter. Let that comparison settle in. 1 atom per cubic centimeter versus 1 atom per cubic meter. That is a factor of approximately 1 million. The space between galaxies is roughly 1 million times emptier than the space between stars. And the space between stars was already the emptiest environment most people can imagine. This is the transition that no photograph prepares you for. The shift from interstellar to intergalactic is not a smooth gradient from empty to emptier. It is a collapse. A freefall from a vacuum so extreme it defies human intuition into a deeper vacuum that defies even the language we use to describe emptiness. At interstellar densities, there is at least the concept of a medium, a measurable substance, a background through which things move. At intergalactic densities, the word medium almost stops applying. You are in a space where the average distance between individual atoms can be measured in meters, where a cubic meter of space, a volume large enough to stand in, contains on average a single hydrogen atom, where a room the size of your bedroom, transported to intergalactic space, would contain roughly 15 to 20 atoms total. That is the void you enter when you leave a galaxy. That is what sits between you and the next island of stars. And the nearest island, the very nearest one, is over 2 million light years away. The Milky Way is your home galaxy, 100,000 light years across, hundreds of billions of stars, and yet even inside it, the dominant feature is emptiness. The stars are scattered like grains of sand across a beach so vast you cannot see from one end to the other. Now, imagine leaving that beach. Imagine walking into the ocean. And imagine the ocean is 1 million times emptier than the sand you just left. No waves, no water, no floor beneath your feet. Just an unbroken expanse of almost nothing, stretching 2.5 million light years to the nearest shore. That ocean is the space between the Milky Way and Andromeda. And Andromeda is the closest major galaxy we have. What you have just learned is only the first layer. Because the distance between the Milky Way and Andromeda, as staggering as it is actually one of the smallest intergalactic distances in the observable universe. Most galaxies are not 2.5 million light years from their nearest large neighbor. Most are separated by tens of millions of light years, hundreds of millions, in some cases, billions. And between them, the same desolate, atomically sparse, featureless intergalactic void stretches on and on without interruption. The images lie to you, the maps lie to you, the casual language of astronomy, which talks about galaxy clusters and cosmic neighborhoods as if they were real communities, lied to you. What the universe actually contains in the overwhelming majority of its volume is nothing. And the galaxies, those bright, beautiful spirals and ellipticals that fill every Hubble image from edge to edge, are exceptions. Tiny, isolated exceptions scattered across an emptiness so total that the human brain cannot simulate it. What comes next will take you from our galaxy to the one across the void. It will show you why 2.5 million light-years is even worse than it sounds, why the phrase nearby galaxy is one of the most misleading terms in all of science, and why even a collision between two galaxies is not what you think it is. It is not a crash, it is not a smash, it is something stranger and, in its own way, far more terrifying. The gap between the Milky Way and Andromeda is waiting. 2.5 million light-years. That is the distance between the Milky Way and the Andromeda galaxy. It is the most quoted number in popular astronomy when people talk about our nearest galactic neighbor. And almost nobody who hears that number understands what it actually means. 2.5 million light-years. Light, traveling at roughly 186,000 miles per second, the fastest anything can move in this universe, takes 2.5 million years to cross that gap. That means the light you see when you look at Andromeda on a clear night left that galaxy before modern humans existed. It was already in transit when our ancestors were chipping stone tools on the plains of Africa. It traveled through intergalactic space for the entire duration of human evolution, and it arrived at your retina tonight. That is not the distance between two nearby objects. That is a chasm measured in geological time at the fastest speed the laws of physics permit. But the number alone is not the problem. The problem is that people hear 2.5 million light-years and compare it to other astronomical distances without grasping the structural difference. Proxima Centauri is 4.25 light-years away. That already felt impossibly far when we measured it earlier. Andromeda is roughly 588,000 times farther. Not twice as far, not 10 times as far, not 100 times as far. Nearly 600,000 times farther than the nearest star. And between here and there, between the edge of the Milky Way and the edge of Andromeda, the void is not populated by other stars you can hop between. It is not an interstellar space with slightly bigger gaps. It is an intergalactic desert where the density of matter drops by a factor of approximately 1 million compared to the space between the stars, you know. There are no suns to refuel at, no planets to land on, no waypoints of any kind. Just the thin, hot, invisible intergalactic medium stretching in every direction, for a distance your mind will never fully simulate. Let me make the distance tangible with a model that does not rely on light years at all. Take the entire Milky Way, 100,000 light years of stars and gas and dust and dark matter, and shrink it down to the size of a dinner plate. A standard ceramic plate, roughly 10 inches across. Everything you know is on that plate. Every star you have ever seen in the night sky. Every constellation. Every planet ever discovered by Kepler or Webb. The sun, the Earth, the entire solar system, all of it exists as an invisibly tiny speck, somewhere on the surface of that plate. Now set that plate on a table. Where does Andromeda go? Andromeda, at this scale, would be another dinner plate, slightly larger than yours, sitting roughly 20 feet away. That might sound close. It's not. 20 feet of empty table between two plates with nothing in between. No other plates, no glasses, no silverware, no crumbs. Just flat, featureless nothing from one plate to the other. And remember, the gap between those plates is 25 times wider than either plate itself. The emptiness between them is the dominant feature, not the objects. That ratio, 25 plate widths of pure nothing, is what the nearest major galaxy actually looks like in true proportion. And at this same scale, the Virgo Cluster, the nearest large galaxy cluster, would sit roughly 450 feet away. That is 1.5 football fields of bare table. The football field distances do not start at Andromeda. They start at the structures beyond it. Stand next to the Milky Way plate and look toward Andromeda. You can see it. It is right there, across the room. And that is exactly why this model is so disturbing. Because 20 feet looks crossable. It looks manageable. But that 20 feet represents 2.5 million light years of intergalactic void. 1 million times emptier than the space inside the plates themselves. The nearest major galaxy is close enough to see in the model, and still impossibly, structurally unreachable in reality. The gap is not a wall. It is a desert, and the desert is emptier than anything your experience can simulate. Now here is the part that very few people think about. Andromeda is the closest large galaxy to the Milky Way. It is the best case, the nearest major neighbor in the entire observable universe. If the best case scenario involves 20 feet of empty table between dinner plates, with the Virgo Cluster sitting 450 feet away across a parking lot of nothing, what does the typical case look like? We will get there. Before we move on, stay at that dinner plate for a moment longer. Because the distance between the Milky Way plate and the Andromeda plate, 20 feet of bare table, hides something the model cannot show you. The experience of crossing it. Most people, when they imagine traveling between galaxies, picture the journey as a very long version of traveling between stars. You leave, you endure a long stretch of blackness, and eventually you arrive. The beginning and the end are the dramatic parts. The middle is boring but finite. You just have to wait it out. That is not what crossing intergalactic space would be like. The middle is not boring. The middle is annihilating. It is so long, so featureless, and so psychologically barren that it would redefine what a human being understands by the word nothing. Here is what would happen if you left the Milky Way at the speed of light, heading directly toward Andromeda. For the first few thousand years, the journey would feel almost familiar. Stars behind you, it's thinning out. The bright band of the Milky Way stretching across your rear view, growing slightly smaller with each passing century. Ahead of you, blackness, but the kind you're used to. The kind where you know stars exist somewhere out there, too far to see individually, but present as a background glow. Then the halo stars end. You pass the last faint red dwarfs orbiting the outskirts of the Milky Way, and you enter the true intergalactic medium. Behind you, the Milky Way is still visible. A faint glowing band, growing smaller but recognizable. Ahead, Andromeda is theoretically there, but it is 2.5 million light years away. You cannot see it as anything more than a barely perceptible smudge, no brighter than it appears from Earth to night. It will stay that way for a very long time. Now the real crossing begins. After 100,000 years at the speed of light, you have traveled a distance equal to the full diameter of the Milky Way. Behind you, your home galaxy has shrunk to a faint oval of light. still visible but noticeably smaller. Ahead of you, Andromeda looks exactly the same as it did when you started. You have covered just 4% of the total distance. The void around you is identical in every direction. There are no stars, no dust, no milestones. Nothing has changed except the angle at which the Milky Way's glow falls on your instruments. After 500,000 years, you have crossed 20% of the gap. The Milky Way behind you has faded to a dim smear of light, barely distinguishable from the background glow of distant galaxy clusters. Andromeda ahead is marginally, immeasurably brighter, but not in any way a human eye could detect. You are deep in the void now. If your instruments failed, if you lost your star charts and your directional references, you would have no way to determine which direction was forward and which was back. The intergalactic medium looks the same everywhere. The darkness is total and uniform. You are a single point of matter moving through a space that contains, on average, 1 atom per cubic meter, and there is nothing within 1,000,000 light years in any lateral direction that would register on any sensor you carry. After 1.25 million years, you reach the halfway point. This is the deepest part of the crossing. The Milky Way and Andromeda are each approximately 1.25 million light years away, in opposite directions. Both are faint, both are tiny. You are as far from either shore as it is possible to be while staying on the direct path between them. In every direction perpendicular to your line of travel, the nearest galaxy of any size is millions of light years away. You are, by any meaningful definition, in the most isolated position a traveler between these two galaxies could occupy. You have been traveling for 1.25 million years, at the speed of light, and you are only halfway there. The return trip from the midpoint to Andromeda takes another 1.25 million years. Slowly, imperceptibly, Andromeda's glow begins to strengthen. The smudge develops structure. A core appears. Faint spiral arms emerge. Stars begin to resolve, first as a general brightening, then as individual pinpricks of light. After 2.5 million years of travel at the maximum speed the universe allows, you reach the outer halo of the Andromeda Galaxy. 2.5 million years, at the speed of light, through a void that contained, for most of the journey, nothing your instruments could detect, nothing your eyes could see, nothing your body could interact with in any way. That is the distance between the two closest major galaxies in the observable universe, and there is no shortcut, no wormhole, no hyperspace bypass. Under the known laws of physics, the intergalactic void simply is what it is. A crossing measured in millions of years at the maximum possible speed, through a medium so sparse it might as well not exist. Every second of those millions of years spent in a darkness so complete that the concepts of direction, progress, and arrival lose their intuitive meaning. This is the part the dinner plate model cannot convey. The plates show you the distance. They do not show you the duration. They do not show you what would feel like to be inside that gap, surrounded by it, swallowed by it, with no landmark to confirm you are moving and no reference point to confirm you are alive. But first, there is something important about the space between those two plates that needs to be said plainly, because this is where the common understanding of intergalactic distance breaks down most completely. Most people, when they picture the gap between galaxies, imagine a scaled-up version of the gap between stars, a longer trip through the same kind of emptiness. But that is wrong in a way that matters. The emptiness between galaxies is not quantitatively different from the emptiness between stars. It is qualitatively different. The character of the void changes when you leave a galaxy. Inside the Milky Way, the interstellar medium has structure. There are dense molecular clouds where new stars are forming. There are regions of ionized hydrogen glowing with ultraviolet energy. There are shock waves from supernovae plowing through the gas and compressing it into new structures. The interstellar medium is sparse, yes, but it is dynamic. Things are happening. Matter is cycling between stars and gas clouds. The medium is part of a living system. The intergalactic medium is not like that. Between galaxies, the gas is a diffuse plasma, mostly ionized hydrogen and helium, heated to temperatures in the range of 100,000 to 10 million degrees. That sounds dramatic, but it is misleading. Temperature at those densities does not mean what it means on Earth. When you have 1 atom per cubic meter and that atom is moving fast, the temperature measurement is high, but there is no heat in any meaningful sense. You could float in the intergalactic medium and freeze to death. The particles are energetic, but there are so few of them that they transfer essentially zero thermal energy to anything they touch. This plasma has no structure, no clouds, no shock fronts, no regions of compression or expansion that create anything recognizable. It is the most featureless environment in the known universe. A traveler crossing it would have no way to mark progress, no milestones, no changes in scenery. The view in front of you would look identical to the view behind you, and the view to the left, and the view to the right. Just blackness, pricked by the faint glow of impossibly distant galaxies that do not visibly grow closer, no matter how long you travel. That is the gap between the Milky Way and Andromeda. Not just far, structurally barren, emptied of almost everything that makes space navigable, survivable, or even describable in human terms. And those two galaxies are considered close. Let me widen the frame. The Milky Way and Andromeda are the two largest members of a collection of galaxies known as the Local Group. The name sounds cozy. It sounds like a neighborhood, a cluster of galaxies gathered together in a shared region of space, maybe orbiting each other, maybe interacting, maybe forming a kind of galactic community. The reality is far lonelier than the name implies. The local group contains at least 134 known galaxies spread across a volume roughly 10 million light-years in diameter. That sounds like a lot of galaxies. It is not relative to the space they occupy. The overwhelming majority of those 134 galaxies are tiny dwarfs. Faint, diffuse collections of a few billion stars or less, many of them so dim they were only discovered in the last 2 decades using advanced survey techniques. Most are satellites of either the Milky Way or Andromeda, orbiting their parent galaxy the way moons orbit planets, except the orbits are measured in hundreds of thousands of light years. The third largest galaxy in the local group is the Triangulum Galaxy, also known as M33. It is roughly 2.7 million light-years from Earth, slightly farther than Andromeda. After that, the members drop steeply in size. The Large Magellanic Cloud, a satellite of the Milky Way, sits about 160,000 light-years away and contains roughly 10 to 20 billion stars. The Small Magellanic Cloud is slightly farther and slightly smaller. Beyond those, the local group is populated by dwarf galaxies so faint that many of them contain fewer stars than a single large globular cluster inside the Milky Way. Now picture the volume these objects occupy. 10 million light years across, 134 galaxies. To return to our dinner plate model, the local group would be a handful of plates and coins scattered across a space roughly 80 feet across, about the width of a gymnasium floor. 2 large plates for the Milky Way and Andromeda, a medium plate for Triangulum, a few saucers for the Magellanic Clouds, and then dozens of tiny coins, some no larger than shirt buttons, sprinkled across that floor. Most of the gymnasium is bare. You could walk across it and step on almost nothing. The coins are real, but the gaps between them are the dominant feature. This is the structure of our local universe at the galactic scale. Not a community, not a neighborhood, an archipelago of objects separated by voids so vast that even light needs millions of years to cross from one island to the next. The word group creates an illusion of proximity that has no physical basis. These galaxies are gravitationally bound to one another, yes, meaning their mutual gravity is strong enough to keep them from drifting apart with the expansion of the universe. But gravitational binding does not mean closeness. It means connection across distance. The Earth is gravitationally bound to the Sun from 93 million miles away. The local group galaxies are bound to each other across millions of light years of intergalactic vacuum. And here is where one of the most famous stories in astronomy needs to be corrected, or at least updated. For decades, the standard narrative was that the Milky Way and Andromeda are on a direct collision course, approaching each other at roughly 100 to 120 kilometers per second, destined to merge in approximately 4 to 5 billion years. This was presented as an established fact in textbooks, documentaries, and popular science articles for more than a decade after measurements by the Hubble Space Telescope in 2012 appeared to confirm a nearly head-on trajectory. In June of 2025, a study published in the journal Nature Astronomy significantly changed that picture. A team led by Tilsa Wala at the University of Helsinki, working with researchers at Durham and Toulouse, used updated data from both the Hubble Space Telescope and the European Space Agency's Gaia spacecraft to run 100,000 simulations of the future trajectories of the Milky Way and Andromeda. They incorporated the gravitational influence of the Large Magellanic Cloud and, critically, included for the first time the full range of observational uncertainties in the measurement of Andromeda's motion across the sky. The result was striking. The probability that the Milky Way and Andromeda will collide within the next 5 billion years, the timeline that had been treated as near certain, dropped to approximately 2%. The broader probability of a collision within 10 billion years came out to roughly 50%. A coin flip. The most likely outcomes in the simulations were either a much later merger in 8 to 10 billion years, or no direct collision at all, with the galaxies executing a close flyby and then separating. The reason the result changed so dramatically comes down to a single measurement that is extraordinarily difficult to make. Andromeda's motion through space has 2 components. There is the radial velocity, which tells us how fast it is moving toward us or away from us along the line of sight. That measurement is relatively straightforward. You examine the light from the galaxy, look at how its spectral lines are shifted, and calculate the speed. Andromeda's radial velocity has been known for over a century. It is approaching us at roughly 110 kilometers per second. The harder measurement is the tangential velocity, the speed at which Andromeda is moving sideways across the sky. This motion is tiny when viewed from 2.5 million light-years away. It amounts to a shift of a few millionths of an arcsecond per year. To detect that, you need instruments of extraordinary precision, measuring positions of objects across spans of many years. The Hubble Space Telescope made the first confident measurement in 2012, and it suggested a nearly head-on approach. But the uncertainties in that measurement were large enough that the true sideways motion could have been significantly different. The Gaia spacecraft, launched by the European Space Agency in 2013, was designed to map the positions and motions of stars with unprecedented accuracy. By tracking stars inside Andromeda itself and comparing their positions across years of observation, Gaia provided a tighter estimate of Andromeda's tangential velocity. It was larger than the Hubble measurement had suggested. Andromeda is not barreling straight toward us. It is drifting at an angle, and that angle matters enormously over 2.5 million light-years. The other critical factor the 2025 study introduced was the Large Magellanic Cloud. This satellite galaxy of the Milky Way is not small. It has a mass of roughly 150 billion solar masses, and it is currently making its first close approach to the Milky Way. As it passes near us, its gravitational pull shifts the Milky Way's own trajectory. The previous collision models had not fully accounted for this. When Sawala's team included the Large Magellanic Cloud's gravity in their simulations, it changed the predicted path of the Milky Way enough to alter the collision probability significantly. The conclusion was that the future of these two galaxies is genuinely uncertain. The void between them is so large, and the variables governing their motion are still measured with enough imprecision that the outcome is a coin flip at best. Two objects that have been falling toward each other for billions of years under the influence of their mutual gravity across 2.5 million light-years may or may not ever actually meet. This matters for our story not because the collision timeline itself is the point, but because it exposes something deeper about the relationship between these two galaxies. Even the nearest major galaxy, the one that is supposedly heading toward us, may not actually reach us within the remaining lifetime of our sun. The gap between the Milky Way and Andromeda is so large, and the uncertainties in how these objects move through space are still significant enough that 100,000 simulations cannot produce a confident answer about whether they will ever touch. That is what 2.5 million light years of intergalactic space means in practice. It means that even a gravitationally bound pair of galaxies approaching each other at over 400,000 kilometers per hour may or may not actually meet. The distance is so vast that it dominates everything. Speed, gravity, trajectory, none of it is enough to make the outcome certain. The void between the galaxies is the controlling factor. But let us assume, for the sake of the next point, that the collision does eventually happen. Whether in 5 billion years or 10, at some point in the far future the Milky Way and Andromeda begin to overlap. Their stars enter the same volume of space. The two galaxies merge. What happens? Most people imagine a catastrophe. Two enormous objects smashing together, stars colliding, planets shattered, explosions on an unimaginable scale. The word collision itself conjures images of destruction, of impact, of things breaking apart in a burst of energy. Almost none of that would happen. When two galaxies collide, the stars inside them almost never touch. The probability of any two individual stars physically hitting each other during a galactic merger is extraordinarily low. so low that in most simulations, out of the hundreds of billions of stars involved, the number of direct stellar collisions is effectively zero. The reason is the emptiness we have been discussing. Stars inside a galaxy are so far apart relative to their own size that even when two galaxies overlap completely, the stars pass through each other's territory like two clouds of gnats merging on a summer evening. The gnats do not collide. There is too much space between them. They simply intermingle, and the two clouds become one larger cloud. No individual gnat was ever in danger. This is what a galaxy collision actually is. Two vast, mostly empty structures passing through each other. Their gravitational fields interact. Stars are tugged onto new orbits. Gas clouds compress and trigger new waves of star formation. The shapes of both galaxies are dramatically disrupted, stretched into tidal tails and bridges and rings. But the stars themselves, the individual suns with their individual planets, are so widely spaced that the merger is, from the perspective of any single star, a non-event. The sky would change slowly over millions of years. New stars would appear in unfamiliar positions. The galactic structure overhead would warp and distort. But your star would not be hit. Your planet would not be destroyed. The collision would be invisible to anyone standing on a surface and looking up, at least for millions of years, until the slow gravitational reshuffling moved your star to a new orbit. This is perhaps the most powerful demonstration of what galaxies really are. Even when two of them occupy the same space at the same time, the stars inside do not notice. That is how empty a galaxy is from the inside. And if the inside of a galaxy is that empty, imagine the emptiness between them. The collision story reveals the central deception at the heart of how people think about galaxies. We treat them as objects, solid things, dense concentrations of matter that can crash into each other. But they are not solid. They are not dense. They are clouds, diffused beyond comprehension, held together by gravity but composed almost entirely of empty space. And when two clouds merge, the experience for any individual particle inside them is hardly different from floating alone in the void. There is a consequence of galaxy collisions and gravitational interactions that brings this point home with disturbing clarity. Not all stars stay inside their galaxies. Some get thrown out. During galactic mergers, during close encounters between galaxies, and even during interactions between stars and the supermassive black holes at galactic centers, individual stars can be accelerated to speeds high enough to escape their home galaxy entirely. These are called hypervelocity stars. They are flung outward at hundreds or even thousands of kilometers per second, fast enough to overcome the gravitational pull of the entire galaxy. And once they escape, they keep going, into the intergalactic void, alone. Astronomers have confirmed the existence of these stars. Some have been detected leaving the Milky Way. Others have been identified in the space between galaxies in nearby clusters. Faint points of light, drifting through the intergalactic medium with no parent galaxy, no stellar companions, no planetary system that we can detect. Just a single star, burning its fuel in the void, surrounded by millions of light years of near emptiness in every direction. Imagine that for a moment. A star like our Sun, ripped from its galaxy by gravitational forces it could not resist. Thrown into intergalactic space at enormous speed. Its planets, if it had any, might have been stripped away during the ejection, or they might still orbit, faithfully circling a star that is now the only significant source of gravity, heat, and light for millions of light years in every direction. a solar system adrift in the void, a candle flame on a raft in the middle of an ocean that stretches to every horizon and beyond. If you stood on a planet orbiting an intergalactic rogue star, the night sky would be almost perfectly black. No Milky Way band, no constellations, no visible stars at all without a telescope. The nearest galaxy would be a faint smudge requiring sharp eyes and dark adaptation to see, if it were visible at all. You would live in a solar system that, for all practical purposes, existed alone in the universe. Your star would shine, your planet would orbit, and beyond the thin warmth of that star's light, the void would extend in every direction, unbroken, featureless, for distances that would take light millions of years to cross. These rogue stars are not common relative to the total stellar population, but they exist. Current estimates suggest that as much as 10 to 50% of all stars in the universe may reside outside of galaxies, scattered through the intergalactic medium as the debris of billions of years of gravitational interactions. They are the loneliest objects in the known universe, and their existence proves something important about intergalactic space. It is not merely a gap between galaxies. It is a place, a real, physical environment where objects can exist, where stars can burn, and where the isolation is so total that even a star, a thermonuclear furnace the size of 1,000,000 Earths, is reduced to irrelevance by the scale of the emptiness surrounding it. If a star can be lost in intergalactic space, invisible and irrelevant despite burning hundreds of millions of tons of fuel every second, then the void between galaxies is not just large, it is large enough to swallow stars without a trace. This reframing changes everything about how you should picture the universe. Galaxies are not buildings in a city. They are not even islands in an ocean. They are wisps, faint arrangements of scattered matter stretched across enormous volumes. And the space between those wisps is emptier than anything inside them by a factor of roughly 1,000,000. The local group is our cosmic vicinity, a handful of wisps drifting within 10 million light years of each other, gravitationally tethered but physically isolated. Most of them are so small and faint, you would never see them without a powerful telescope. The two large spirals, our Milky Way and Andromeda, dominate the group, but even they are separated by a gulf so wide that light from one takes 2.5 million years to reach the other. And the local group itself is isolated. Beyond it, the next significant concentration of galaxies is the Virgo Cluster. It sits approximately 54 million light-years away. 54 million. That is more than 20 times the distance from here to Andromeda. More than 5 times the diameter of the entire local group. Between us and the Virgo Cluster, there are scattered galaxies, small groups, thin filaments of the cosmic web. But the dominant feature of that 54 million light-year span is emptiness, intergalactic void. The same thin, structureless plasma we described earlier, stretching across a distance so large that the Milky Way to Andromeda gap, the one that already defied comprehension, could fit inside it more than 20 times over. And the Virgo Cluster is considered our local neighborhood on the cosmic scale. When astronomers talk about the large-scale structure of the universe, they use phrases like nearby cluster and local supercluster. These words mean something specific in astrophysics. They refer to gravitational relationships and relative proximity on a cosmic scale. But they communicate something very different to a general listener. They communicate closeness, familiarity, a sense that the Virgo Cluster is just over there, that the universe is neatly organized into accessible zones. It is not. The Virgo Cluster is 54 million light years of intergalactic nothing away from you. At the speed of light, that trip takes 54 million years. At the speed of our fastest spacecraft, roughly 40,000 miles per hour, it would take roughly 900 billion years. More than 60 times the current age of the universe. The Virgo Cluster is not next door. It is not across town. It is so far away that no technology conceivable under known physics could deliver a human being there within the lifespan of our species. And the Virgo Cluster is still close by cosmic standards. The observable universe extends roughly 46 billion light years in every direction. The Virgo Cluster sits in the very near foreground of that expanse. It is a tiny step away from home on the map of the full cosmos. And even that tiny step involves crossing 54 million light years of intergalactic void. This is the reality that begins to emerge when you move from the interstellar scale to the intergalactic scale. Distances stop being large versions of familiar distances. They become something else entirely. They become structural. The emptiness between galaxies is not a travel problem. It is an architecture problem. The universe is built with voids as its primary material and galaxies as rare decorations scattered along thin threads of structure. And as we zoom out further, as we look beyond the Virgo Cluster and out toward the full cosmic web, the voids do not shrink, they grow, and the galaxies do not fill them. They retreat to the margins, clinging to filaments and walls that are themselves separated by abysses hundreds of millions of light years across. The gap between the Milky Way and Andromeda was the first step. The gap between the local group and the Virgo Cluster was the second. What comes next is the view from above, the map of the universe at its largest scale. And that map will show you that everything we have discussed so far, the galaxies, the groups, the clusters, all of it, occupies a vanishingly thin fraction of the total volume. The rest is void. And the voids are not gaps in the structure, they are the structure. We cross the gap between the Milky Way and Andromeda. 2.5 million light years of intergalactic void. We stood inside the local group and saw that even our immediate cosmic neighborhood is a scattering of objects separated by enormous distances, bound together by gravity but isolated by space. And we ended on a number, 54 million light years. The distance to the Virgo Cluster, the nearest large collection of galaxies beyond our local group. Now we go there. And when we arrive, what we find is not what you might expect. The Virgo Cluster is one of the most studied galaxy clusters in the sky. It contains approximately 1,500 galaxies. Some estimates place the number closer to 2,000 when faint members are included. It is the gravitational heart of a much larger structure called the Virgo supercluster, which itself contains at least 100 galaxy groups and clusters spread across roughly 147 million light years. Our own local group sits on the outskirts of this supercluster, drifting slowly inward, pulled by the combined gravity of everything the Virgo cluster contains. 1,500 galaxies. That number, on first hearing, sounds impressively dense. It sounds like the Virgo cluster must be a crowded, turbulent place, galaxies packed together in a roiling mass of stars and light. And compared to the local group, it is dense. But the word dense, like the word nearby, is doing deceptive work in this context. The Virgo cluster spans roughly 15 million light years from one side to the other. 15 million light years of volume, holding 1,500 galaxies. To understand what that density actually feels like, imagine a cathedral. Not a small parish church, a grand European cathedral, the kind with vaulted ceilings rising hundreds of feet above the floor and a nave stretching the length of a city block, now scatter 1,500 dust motes through the air inside that cathedral. Not 1,500 per cubic foot, 1,500 total, spread from the entrance to the altar, from the floor to the peak of the highest arch. You would not see them, you would not feel them. If you walked through the cathedral, you might pass within a few feet of one or two, but most would be invisible to you, too small and too widely spaced to register. The cathedral would look and feel empty. The dust motes are real. They are there. But they are irrelevant to your experience of the space. The space dominates. That is what the Virgo Cluster is like from the inside. 1,500 galaxies scattered through a volume 15 million light years across. The average separation between neighboring galaxies in the cluster is measured in hundreds of thousands to millions of light years. Galaxies at the dense core of the cluster are closer together, perhaps a few 100,000 light years apart. Galaxies at the periphery are separated by gaps that rival the distance from the Milky Way to Andromeda. And here is the detail that sharpens this picture. Each of those 1,500 galaxies is itself mostly empty space, as we established earlier. The Virgo Cluster is not a dense knot of matter. It is a collection of wisps, each wisp made of scattered stars separated by light years, the whole collection spread through a volume that would take light 15 million years to cross. Matter, in any form you would recognize, occupies a vanishingly small fraction of the cluster's total volume. The rest is void, hot, thin intracluster gas, dark matter scaffolding, and emptiness. The dominant galaxy in the Virgo Cluster is M87, a giant elliptical galaxy sitting near the cluster's center. M87 is enormous by galactic standards. It contains roughly 1 trillion stars and hosts a supermassive black hole with a mass of roughly 6.5 billion times the mass of our Sun. It was the target of the first ever direct image of a black hole shadow, captured in 2019 by the Event Horizon Telescope. M87 is one of the most massive galaxies in the local universe. And even M87 is a wisp. 1 trillion stars spread across a volume roughly 120,000 light years in diameter. The stars inside it are no closer together than the stars inside our own galaxy. M87 just has more of them, scattered across a comparable or slightly larger volume. From the inside, it would look like any other galaxy. Stars separated by light years, darkness between them, structure defined by absence rather than presence. This is the recurring theme that becomes inescapable as you scale outward. At every level, from solar systems to galaxies to galaxy clusters, the dominant feature is not the matter. It is the space between the matter. And at every level, that space grows more extreme. The ratios shift further and further toward emptiness. By the time you reach the scale of galaxy clusters, you are looking at structures where the matter content, if compressed into a solid block, would occupy a volume so tiny relative to the whole that it would be invisible. Now, let us leave the Virgo Cluster and keep going, because the Virgo Cluster is not the end of the story. It is one node in a much larger architecture, and that architecture has a shape that, when you see it clearly, changes the way you think about the universe forever. If you could somehow rise above the Virgo Cluster and look down at the universe from a height of a few 100 million light years, what you would see is not a uniform scattering of galaxies. you would see a pattern, a vast, intricate, three-dimensional network of filaments, walls, and nodes threaded through with enormous empty regions. This pattern has a name. It is called the cosmic web. The cosmic web is the largest structural pattern in the known universe, and its discovery was an accident that stunned the scientists who made it. In the late 1970s and early 1980s, galaxy surveys were still crude by modern standards. Astronomers would point their telescopes at patches of sky, record the positions and brightnesses of galaxies, and then measure their redshifts one at a time to estimate how far away each one was. The process was slow. A single night of observing might yield a few dozen distances. Building a three-dimensional map of even a small wedge of the universe took years. In 1986, astronomers Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics, known as the CFA, published a map that changed the field overnight. They had been conducting a systematic redshift survey of galaxies in a thin strip of sky, measuring the distances to more than 1,000 galaxies and plotting their three-dimensional positions. When they looked at the completed map, they expected to see a roughly uniform scattering of points, perhaps with some mild clustering. Galaxies were known to clump together in groups and clusters, but the prevailing assumption was that on sufficiently large scales, the distribution would smooth out into something random and featureless. That is not what the map showed. What Geller and Huchra saw was a pattern so striking it looked artificial. Galaxies were not scattered randomly. They were arranged along thin walls and filaments that surrounded enormous empty regions. The structure looked like a cross-section through a network of bubbles, with galaxies lining the bubble surfaces and virtually nothing inside. One particular concentration of galaxies formed an arc so prominent that the team nicknamed it the Great Wall, and the voids it bordered were not subtle dips in the galaxy count. They were vast, unmistakable emptinesses, regions hundreds of millions of light years across, where the galaxy density dropped to nearly zero. The map became famous partly for its shape. The survey wedge, plotted in polar coordinates with distance radiating outward from the center, bore a rough resemblance to a human stick figure with outstretched arms. The astronomy community began informally referring to it as the Stick Man. But the fame was not about the shape. It was about what the shape revealed. The universe had structure on scales far larger than anyone had anticipated. And that structure was defined not by where the galaxies were, but by where they were not. The voids were not gaps in the data. They were the dominant features. The galaxies merely traced the edges. Geller described the reaction in the scientific community as shock. The expectation had been homogeneity. The reality was a cosmos organized into a complex filamentary architecture where emptiness was the rule and matter was the exception. In the decades that followed, every major galaxy survey confirmed and extended this finding. The 2-degree field galaxy redshift survey mapped hundreds of thousands of galaxies and found the same web. The Sloan Digital Sky Survey pushed the map to millions of galaxies across billions of light years and found the same web at every scale. The pattern was not a local anomaly. It was the universal architecture of everything. That soap bubble analogy is one of the most accurate visual descriptions in all of cosmology. Imagine a mass of soap bubbles, the kind you can make by blowing through a ring dipped in dish soap. Each bubble has a thin film of soapy water forming its walls. Where bubbles meet, the walls merge into thicker ridges. Where 3 or more bubbles intersect, the ridges converge into dense knots. The interior of each bubble is air, nothing but empty space enclosed by the thinnest possible membrane. Now scale that up to the universe. The thin walls of the bubbles are the cosmic web filaments and sheets, made of galaxies, gas, and dark matter. The dense knots where filaments intersect are the galaxy clusters, like the Virgo Cluster. And the interiors of the bubbles are the cosmic voids, regions of space tens of millions to hundreds of millions of light years across, containing almost nothing. This is not a metaphor. This is the measured shape of the universe. Every major survey conducted since has confirmed the same architecture, extending it to billions of light years in every direction. The web is real. It is measured. And its implications for the question of intergalactic emptiness are devastating. Here is the number that matters most. Approximately 80% of the total volume of the universe is void. 80%. 4/5 of everything. The filaments, walls and clusters that contain the galaxies, all the bright, interesting populated structures in the cosmos, occupy roughly 10 to 20% of the total volume. The rest is empty. And that empty 80% is not mildly empty. It is profoundly, structurally empty, with matter densities that are a fraction of the cosmic average, which itself is already almost nothing. Let me state that differently to make sure the weight of it lands. If you picked a random point in the universe, a truly random location selected with no bias toward galaxies or filaments or clusters, there is roughly an 80% chance that you would find yourself in a cosmic void, not near a galaxy, not in a filament, not close to anything recognizable as a structure. You would be adrift in a region of space where the nearest galaxy might be tens or hundreds of millions of light years away, and the density of matter around you would be lower than the already astonishing intergalactic average. The galaxies that fill every Hubble photograph from edge to edge are not the universe. They are decorations on the margins of the universe. The actual universe, the majority of its volume, is the void between them. This inverts the picture most people carry in their heads. When someone imagines the cosmos, they imagine galaxies, spirals, ellipticals, irregular blobs of light. They picture a sky full of them, a universe defined by its galaxies with some gaps here and there. The reality is the opposite. The universe is defined by its voids, with some galaxies here and there. The voids are not the background, they are the foreground. The galaxies are the rare, thin, fragile exceptions, clinging to the edges of an emptiness so total it accounts for the vast majority of everything that exists. Now, let me take you inside one of those voids, the most famous one. The one that, when you hear its dimensions, will make even the Milky Way to Andromeda gap feel modest. The Boötes void was discovered in 1981 by American astronomer Robert Kirshner and his colleagues. It sits roughly 700 million light years from Earth in the direction of the constellation Boötes. When Kirshner's team mapped the galaxy distribution in that region, they found something disturbing. A spherical region of space approximately 330 million light years across that was almost completely empty of galaxies. 330 million light years. That is more than 3,000 times the diameter of the Milky Way. More than 130 times the distance from here to Andromeda. A volume of space so large that if you place the entire local group, all 10 million light years of it, inside the Boötes void, it would be a tiny speck. occupying a fraction of a percent of the void's total volume. In a region that size, astronomers would normally expect to find several thousand galaxies. The BO-OHT's void contains roughly 60 galaxies in a sphere 330 million light-years wide. They are not clustered together. They are distributed in a thin, roughly tubular arrangement, threading through the void's center, possibly remnants of smaller voids that merged over billions of years to create this single, enormous, empty region. If you were placed at the center of the BO-OHT's void, and you looked in every direction, you would see nothing. No galaxies visible to the unaided eye. No bright structures of any kind. Just blackness, stretching for more than 160 million light-years in every direction before the first faint galaxies along the void's boundary came into view. And even those boundary galaxies would not look like much. They would be faint, distant, barely distinguishable from the darkness behind them. The BO-OHT's void is the largest confirmed void in the observable universe, but it is not unusual in principle. Cosmic voids are everywhere. They are the most common large-scale structures in existence precisely because they dominate the volume. Typical voids range from 30 to 300 million light-years across. Some are rounder, some are elongated. Some are connected to each other through thin passages where the filament walls separating them have thinned to almost nothing. The universe seen on this scale looks less like a web and more like a foam. Bubbles within bubbles within bubbles, each one a vast region of near emptiness surrounded by thin walls of galaxies. The BO-OHT's void is the most famous void in astronomy, but it is not alone. It is not even the most unsettling. In 2007, astronomers studying data from the Wilkinson Microwave Anisotropy Probe identified an unusually cold region in the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. This cold spot sat in the direction of the constellation Eridanus and was significantly colder than the surrounding background, suggesting that the light had passed through a region of space with far less matter than average. Follow-up surveys confirmed the suspicion. The Eridanus supervoid is a vast underdense region, roughly 500 million to a billion light-years across, depending on how its boundaries are defined. It is one of the largest structures, or rather anti-structures, ever identified. A region so empty and so vast that it left a measurable imprint on the oldest light in the universe. The relationship between the cold spot and the void is still debated. Some researchers argue the void alone is not large enough or empty enough to fully explain the temperature anomaly. Others suggest additional physics, possibly involving dark energy's behavior inside voids, may be required. But the void itself is confirmed. It exists. It is enormous. And it is one of many. Even more provocative is a hypothesis that has gained attention in recent years. Some researchers have proposed that our own local group sits near the edge of a very large underdense region informally called the KBC void, named after the astronomers Keenan, Barger, and Cowie, who characterized it. This proposed void would be roughly 2 billion light-years across and would have a matter density roughly 20 to 40% below the cosmic average. If real, it would mean that the galaxy distribution we see in our immediate cosmic vicinity is not representative. We would be living in an unusually sparse region, looking out at a universe that is, on average, slightly denser than our surroundings suggest. The KBC void is not universally accepted. Some analyses of galaxy surveys and cosmic microwave background data are consistent with it. Others find no strong evidence for such a large local underdensity. The debate is ongoing, but the fact that the hypothesis exists and is taken seriously by working cosmologists illustrates something important about the nature of voids. They are not rare oddities at the margins of the cosmos. They are pervasive. They come in all sizes. They overlap, merge, and nest inside one another. And they dominate the volume of the universe so thoroughly that the question is not whether we are near a void, but how deep inside one we happen to sit. Every new galaxy survey that pushes to greater depths and wider coverage finds more voids. The universe is riddled with them. They are separated by the thinnest possible membranes of galaxies, and in some places those membranes have thinned to almost nothing, leaving passages where one void connects directly to another, creating cavities within cavities that stretch across billions of light years. And those thin walls, those filaments and sheets that hold the galaxies, are themselves not what you might picture. When you hear the word filament, you might imagine something dense, a rope, a cable, a thick strand of material connecting 2 points. Cosmic filaments are not like that. They are enormous in length, stretching 50 to 100 million light years or more. But they are narrow, typically just a few million light years across, and the galaxies within them are scattered along their length the way rest stops are scattered along a highway crossing a continental desert. You drive for hundreds of miles through empty land, and then a small cluster of buildings appears. You pass through it in moments, then the emptiness resumes, and you drive for hundreds of miles more before the next one. The filaments of the cosmic web are those highways. The galaxies are the rest stops, and the desert between the highways, the interior of the voids, is where 80% of the universe's volume lies. Most of the journey, no matter which direction you travel, is through nothing. This is the architecture of the cosmos. Not a city of galaxies, not even a network of connected towns. A thin, fragile scaffolding of thread-like structures draped across an abyss so vast that the scaffolding itself accounts for only a minority of the total space. The universe is built out of emptiness. The matter is an afterthought, a residue left behind by the gravitational processes that shape the voids. And the voids are still growing. Because the universe is expanding, and because voids contain less matter than the regions around them, they experience less gravitational drag against that expansion. Voids expand faster than the cosmic average. Over billions of years, they grow larger and emptier while the filaments between them are compressed and thinned. The galaxies along the filaments are pulled inward toward the clusters at the filament intersections, and the voids behind them stretch wider. This process has been operating since the universe was young. The tiny density fluctuations imprinted in the cosmic microwave background, the faint afterglow of the Big Bang, seeded both the overdense regions that would become filaments and clusters and the underdense regions that would become voids. Gravity amplified those initial differences over 13.8 billion years. Matter flowed out of the underdense regions and into the overdense ones. The rich got richer, the empty got emptier, and the result is the universe we see today. A cosmos where the average density is roughly 1 atom per cubic meter. But that average is profoundly misleading because it combines the relatively higher density inside filaments with the far lower density inside voids, producing a number that describes almost nowhere in particular. Inside the filaments, near galaxies and clusters, The density rises to 10, 100, sometimes 1,000 times the cosmic average. But inside the great voids, the density drops to a fraction of that average. The deepest voids may have densities as low as 10 to 30% of the mean, which itself is already almost nothing. A void with a density of 20% of the cosmic average contains approximately 1 atom per 5 cubic meters. A volume the size of a small car holding a single hydrogen atom. This is the environment that fills most of the observable universe, not the glowing filaments, not the bustling clusters, not the majestic spirals. The default state of the cosmos is a void. Thin, dark, featureless, expanding, and almost perfectly empty. Our own position in this structure is worth noting. The Milky Way is not inside a void. We sit in a small filament of the cosmic web that connects the Fornax cluster to the Virgo Cluster. Our local group is on the outskirts of the Virgo supercluster, which is itself part of an even larger structure identified in 2014 called Laniakea, a Hawaiian term meaning immense heaven. Laniakea is a supercluster containing roughly 100,000 galaxies spread across 520 million light-years. The Virgo cluster sits near its center. The local group sits near its edge, falling slowly inward. But even Laniakea, this immense heaven of 100,000 galaxies, is mostly void. The galaxies within it are distributed along filaments and walls that surround interior voids, the same bubble-like architecture seen everywhere else. And Laniakea itself is bordered by other superclusters separated by voids so large they make the Boötes void look modest. The point of all of this, the reason we have spent so long walking through filaments and voids and superclusters is not to impress you with large numbers. The numbers are impressive, but they are not the lesson. The lesson is structural. Galaxies are not scattered through the universe the way people imagine. They are not distributed like stars in a galaxy, with moderate, comprehensible distances between them. They are confined to a thin, thread-like skeleton of filaments and walls that occupies a small minority of the total volume of space. Between those threads, the voids stretch on and on, hundreds of millions of light-years of near nothing, growing emptier as the universe ages. And the galaxies on those threads are themselves islands. Each one is isolated by millions of light-years of intergalactic vacuum from its nearest neighbor. Each one is a wisp of stars adrift in the void, clinging to a filament the way a droplet of morning dew clings to a strand of spider silk. Real, but tiny. Present, but barely there. Surrounded on all sides by an emptiness that dwarfs it by every conceivable measure. When you look at a Hubble Deep Field and see 10,000 galaxies piled into a single image, what you are really seeing is every droplet of dew on a web that stretches across a field miles wide, compressed into a single photograph. The web is real. The dew is real. But the field, the vast empty space between the strands, is the thing that defines the landscape. Remove the field and the web has no meaning. Remove the voids and the cosmic web collapses into a featureless smear. The universe is not made of galaxies. It is made of the space between galaxies. The galaxies are merely what we notice because they shine. The voids do not shine. They do not appear in photographs. They cannot be seen, only inferred from the absence of light. And so we build our picture of the cosmos from the exceptions and ignore the rule. The rule is emptiness. The rule is void. The rule is a darkness so uniform and so vast that the bright islands of stars and gas we call galaxies are barely a rounding error in the total volume of the universe. What comes next will take you back inside that void. Not the void of the Boötes region or any other named structure, but the generic, default void of intergalactic space. The space you enter the moment you leave a galaxy. The space that contains almost half of all the ordinary matter in the universe, yet spreads it so thin that it might as well be nothing. The space that makes galaxies what they truly are. Not the universe's neighborhoods, not its cities or villages or settlements, its islands, small, bright, impossibly remote islands, separated by an ocean of silence that stretches in every direction, farther than any human mind can follow. Everything we have built across this story has been leading here. We started inside the Milky Way and discovered that even a galaxy full of hundreds of billions of stars is overwhelmingly empty. We crossed the gap to Andromeda and found that the nearest major galaxy is separated from us by 2.5 million light years of structureless void. We surveyed the local group and learned that our cosmic neighborhood is a sparse scattering of objects drifting through 10 million light years of near nothing. We zoomed out to the Virgo Cluster, the cosmic web, and the great voids, and we found that 80% of the universe's volume contains almost no galaxies at all. Now we go into the void itself. Not to gawk at its size. We have done that. Now we go in to understand what it contains. Because intergalactic space is not perfectly empty, it holds something. And what it holds is one of the strangest substances in the known universe. A material that accounts for roughly half of all the ordinary matter that exists, yet is so diffuse that it took scientists decades to confirm it was even there. It is called the warm-hot intergalactic medium, sometimes abbreviated as the WHIM, and its story reveals the final layer of what makes intergalactic space so profoundly, structurally desolate. For decades, cosmologists faced an embarrassing problem. When they added up all the ordinary matter they could see in the universe, the stars, the gas inside galaxies, the hot plasma in galaxy clusters, the total came up short. Significantly short. The amount of ordinary matter predicted by models of the Big Bang and confirmed by measurements of the cosmic microwave background was roughly twice what astronomers could actually account for. Half of the baryons, the protons and neutrons that make up everything you can touch and see, were missing. Not dark matter. Dark matter is a separate category, an invisible substance that interacts with ordinary matter only through gravity. The missing baryons were ordinary matter, the same hydrogen and helium that make up stars and gas clouds. Half of it simply could not be found. The theoretical prediction was that the missing matter had to be hiding in the intergalactic medium, the space between galaxies. Computer simulations of cosmic structure formation showed that as the universe evolved, gas falling into the filaments and voids of the cosmic web would be shock heated to temperatures between 100,000 and 10 million degrees Kelvin. At those temperatures, hydrogen is almost fully ionized. It loses its electron and becomes a bare proton, transparent to most wavelengths of light. It does not glow visibly. It does not absorb starlight in ways that are easy to detect. It becomes, for all practical purposes, invisible. This was the warm-hot intergalactic medium, a vast diffuse plasma filling the space between galaxies, heated to extraordinary temperatures but spread so thin that detecting it directly was one of the hardest observational challenges in modern astronomy. In 2018, a team led by Fabrit CO Nicastro published results in the journal Nature confirming the detection of the WHIM using the European Space Agency's XMM Newton satellite. By studying the X-ray spectrum of a distant quasar, they identified absorption signatures of highly ionized oxygen in the intergalactic medium along the line of sight. The absorbers sat in regions of elevated galaxy density, consistent with the filamentary structure of the cosmic web. The amount of missing baryonic matter implied by the detections matched the predictions. The missing baryons had been found. They were exactly where the simulations said they would be, hiding in the hot, thin gas between galaxies. This was a major discovery. It closed one of the longest-standing gaps in our inventory of the universe's contents. But from the perspective of our story, the discovery carries a different weight. Because what it tells us is that roughly half of all the ordinary matter in the universe, half of every proton and neutron that exists, is spread across the intergalactic void in a state so diffuse that humanity needed decades of technological development just to confirm it was real. Think about what that means. The stars, the planets, the galaxies, everything that shines, everything you can see through any telescope ever built, accounts for only a portion of the universe's ordinary matter. A comparable amount is floating between the galaxies in a plasma so thin it has a density of roughly 1 to 10 particles per cubic meter. Those particles are moving fast, which is why the temperature measurement is high, but there are so few of them that the medium transfers essentially no energy to anything it touches. It is simultaneously millions of degrees hot and functionally colder than anything you have ever experienced. A human being placed in the warm, hot intergalactic medium would not burn. They would freeze. The particles are energetic, but they are so sparse that the thermal energy they carry is negligible. Your body would radiate its own heat into the void and receive almost nothing in return. This is the substance that fills the space between galaxies. Not nothing. Something. But a something so attenuated, so stretched across such incomprehensible volumes, that it might as well be nothing for any practical purpose. You cannot breathe it. You cannot use it for fuel. You cannot collect it in any meaningful quantity without sweeping across volumes measured in light years. It exists as a ghost of matter, a thin residue of the universe's formation, spread across the void like a single drop of ink, dissolved in an ocean. And there are no landmarks in it, no structure, no variation you could use to navigate or orient yourself. The WHIM has large-scale density gradients, denser near filaments, and sparser deep inside voids, but those gradients play out over millions of light years. At the scale of a traveler, the medium is uniform, featureless, the same in every direction. You could travel through it for 1,000,000 years at the speed of light, and the view would not change. The density would not shift perceptibly. No star would appear ahead of you. No structure would loom on the horizon. The galaxies you left behind would have faded to invisibility long ago. The galaxies ahead would not yet be visible. You would be suspended in a darkness that contains technically something, but offers functionally nothing. This is the environment that separates every galaxy from every other galaxy. Not vacuum in the colloquial sense, not the clean, empty black space of science fiction, punctuated by the occasional asteroid or nebula. Intergalactic space is a featureless, landmark-free expanse of ultra-thin plasma stretching across distances that make even the word distance feel inadequate. It is not a gap you cross. It is a condition you endure, and it endures for millions of light years in every direction, from every galaxy that exists. Now, step back. Hold all of this in your mind at once. The cosmic web, with its filaments and voids, the voids dominating 80% of the volume. The filaments holding the galaxies but stretching them thin, like rest stops scattered along highways that cross deserts millions of light years wide. The galaxies themselves, mostly empty space inside. The intergalactic medium filling the gaps with a plasma so diffuse, it took decades to find. And at the center of all of it, one fact that does not soften no matter how many times you encounter it. Galaxies are islands. That word, islands, has been used loosely in astronomy for over a century. The phrase island universes was coined in the 18th century to describe the idea that the nebulae visible in telescopes might be other galaxies, separate systems of stars floating in a larger void. When Edwin Hubble confirmed in the 1920s that the Andromeda Nebula was indeed a separate galaxy millions of light years away, the island metaphor became literal. Galaxies are islands of stars surrounded by an ocean of intergalactic space. But most people do not follow the metaphor to its conclusion. When you think of an island, you think of land surrounded by water. The water is navigable. You can sail across it. You can see other islands from the shore. The ocean between islands is full of life, full of waves, full of weather. It is a medium, a connective tissue that links the islands together even as it separates them. The intergalactic void is not that kind of ocean. It connects nothing. It sustains nothing. It contains, in practical terms, nothing that can be used, harvested, or navigated by. A galaxy sitting in intergalactic space is not an island in a busy sea. It is a lighthouse perched on a rock in the middle of an ocean so vast that no other lighthouse is visible from its lantern room. The nearest light is below the horizon, hidden by the sheer curvature of distance. The ocean stretches to the horizon in every direction, and beyond the horizon it continues, and beyond that it continues further, and the water is not water but an emptiness so complete that even the concept of crossing it begins to lose coherent meaning. Every galaxy in the universe is that lighthouse, shining alone, surrounded by millions of light years of void, aware, if awareness is possible, that other lighthouses exist somewhere out there in the dark, but unable to reach them, unable to see them without instruments of extraordinary power, unable to confirm their existence except through faint signals that took millions of years to arrive and will take millions more to answer. This is the picture that collapses when you truly understand intergalactic space. The picture that most people carry, the comfortable one, is a universe that is large but populated. A cosmos full of galaxies, close enough to interact, close enough to form a coherent community. The deep field images reinforce this. The cosmic maps reinforce this. The language of astronomy, with its groups and clusters and superclusters, reinforces this. Everything about how we communicate the structure of the universe emphasizes the nodes and ignores the gaps. But the gaps are the universe. The nodes are the exception. And the exceptions are so small, so fragile, so widely spaced that the word isolated does not begin to capture their situation. Consider the Milky Way. Our galaxy is one of the two largest members of the local group. It is gravitationally bound to roughly 134 other galaxies. It sits in a filament of the cosmic web. It is falling toward the Virgo Cluster. By galactic standards, it is well connected. It has neighbors. It has gravitational relationships. And yet, the nearest major galaxy is 2.5 million light-years away. The nearest large cluster is 54 million light-years away. The supercluster we belong to, Laniakea, stretches 520 million light-years across and is bordered on all sides by voids. Beyond those voids are other superclusters, separated by more voids. And between all of these structures in every direction, the warm, hot intergalactic medium stretches on in silence. No spacecraft we have ever built, or could build with known physics, will cross even the smallest of these gaps within the lifetime of human civilization. Voyager 1, the farthest human-made object from Earth, is traveling at roughly 38,000 miles per hour. At that speed, it would take roughly 44 billion years to reach Andromeda, more than 3 times the current age of the universe. And Andromeda is the closest major galaxy. The Virgo Cluster would take almost 1 trillion years. The far side of the Bo-OHT's void would take longer than any number that has physical meaning. These are not engineering problems waiting for better technology. They are structural features of the universe. The cosmos is built at a scale where even the speed of light is slow, where even the gravitational pull between galaxies takes billions of years to produce meaningful motion, where the distances between structures are so large that the structures themselves are, for all practical purposes, permanently isolated from each other, not temporarily separated, not waiting to be connected by some future technology, structurally alone. This is the truth that hides behind every beautiful galaxy image. The universe is not a web of connected neighborhoods. It is an archipelago of unimaginable loneliness. Each island shines. Each one contains billions of stars and potentially billions of worlds. But the ocean between the islands is so vast, so empty, and so featureless that crossing it is not merely difficult. It is, under the known laws of physics, effectively impossible on any timescale meaningful to life. And the universe is making it worse. Because the expansion of the cosmos is accelerating. Driven by dark energy, the space between galaxy clusters is growing. Voids are widening, filaments are stretching. The cosmic web is slowly being pulled apart. Over billions of years, galaxies that are not gravitationally bound to each other will recede beyond each other's observable horizons. Their light will be redshifted beyond detection. Their existence will become unknowable. The local group will remain bound. The Milky Way and its immediate companions will persist together, eventually merging into a single large elliptical galaxy. But the Virgo Cluster, the other superclusters, the far-flung galaxies we see today in every deep field image, will fade from the sky one by one. Not because they are destroyed, because the space between us and them will have expanded so much that their light can no longer reach us. Let me walk you through what that future actually looks like, step by step, because the timeline matters. It is not a sudden event. It is a slow, silent erasure that unfolds across billions of years. Right now, when you point a powerful telescope at the sky, you can see galaxies billions of light years away. Their light is old. It has been traveling for most of the age of the universe, but it is still arriving. The photons are still reaching your instruments. The information they carry, the colors, the spectra, the redshifts, is still readable. From those photons, you can deduce the expansion rate of the universe, the distribution of matter, the existence of dark energy, the age and geometry of the cosmos. The universe is telling you its story through the light that arrives from distant sources. Right now, the story is still being delivered. In roughly 2 billion years, The Milky Way will likely merge with the Large Magellanic Cloud. The local group's internal dynamics will continue. Small dwarf galaxies will be absorbed. Stars will be traded between the remaining members. The local group will consolidate. This part of the future is gravitationally determined and relatively straightforward. On a longer timescale, the Milky Way and Andromeda, whether they collide in 5 billion years or 10, will eventually merge. The result, after a few billion years of gravitational settling, will be a single large elliptical galaxy. No more spiral arms, no more distinct disk, just a massive, slowly rotating collection of old stars bound together by gravity. Astronomers have nicknamed this future galaxy Milkomeda. It will be the dominant object in what remains of the local group. Now look outside the local group. The Virgo Cluster, 54 million light-years away, is not gravitationally bound to us with enough strength to resist the expansion of space. Over billions of years, the space between the local group and the Virgo Cluster will grow. The cluster will appear to recede. Its light will stretch to longer wavelengths. The galaxies within it will redden, dim, and eventually fall below the detection threshold of any conceivable instrument. This process will not happen overnight. It will unfold across tens of billions of years, but it is relentless. Each year, the gap between us and every unbound structure grows slightly wider. Each year, the light from those structures arrives slightly more redshifted. The most distant galaxies we can see today, the ones at the edge of the observable universe, are already receding from us faster than the speed of light because the space between us is expanding faster than light can cross it. We see them only because their light was emitted long ago, when the gap was smaller. No new light from those galaxies will ever reach us. They are already, in a sense, gone. Over the next 100 billion years, the same fate will befall every galaxy and cluster that is not gravitationally bound to our local group. One by one, they will cross the cosmological horizon. Their light will stretch to infinite wavelength. Their images will freeze, redden, dim, and vanish. The cosmic microwave background itself, the afterglow of the Big Bang, will redshift beyond detection, cooling to a temperature so close to absolute zero that no instrument could distinguish it from perfect emptiness. And then the sky will be dark. Not dark the way it is now, where darkness is punctuated by distant galaxies visible through telescopes. Dark in the absolute sense, a sky containing nothing except the stars of your own merged galaxy, Milkomeda, slowly aging, slowly dimming, slowly burning through the last of their fuel. A civilization arising in that far future, tens of billions of years from now, looking up at the sky from within Milkomeda, would see a single galaxy surrounded by infinite blackness. They would have no evidence of the cosmic web, no evidence of other galaxy clusters, no evidence of the expansion of the universe, no cosmic microwave background to measure, no distant supernovae to calibrate against. Every clue that the cosmos extends beyond their island, every piece of evidence that the universe has a history of expansion and cooling and structure formation will have been carried beyond the horizon. Those future astronomers, if they arise, will construct a model of the universe based on what they can observe. And what they can observe will be a single galaxy, static and alone, floating in an empty cosmos that appears to have no beginning and whose structure. They will not know about the Big Bang. They will not know about dark energy. They will not know about the billions of galaxies that once filled the sky. The universe will have erased its own history by expanding the evidence beyond the reach of observation. This is not a thought experiment. It is the mainstream prediction of cosmology under the lambda CDM model, the same model that has passed every observational test thrown at it for more than 2 decades. The universe is heading toward a state of absolute isolation. Not the isolation of one galaxy from its neighbor. The isolation of every gravitationally bound structure from every other one. Total, permanent, unknowable from the inside. The evidence will not be hidden. It will not be encrypted or obscured. It will be gone, expanded beyond the reach of light itself. The universe will look empty, not because it is empty, but because everything beyond the local horizon will have been carried away by the growth of space at a rate no signal can overcome. We live in the only era of cosmic history where the true structure of the universe is visible, where the light from distant galaxies still reaches us, where the cosmic microwave background still carries the fingerprint of the Big Bang, where the redshifts of distant objects still reveal the acceleration of expansion. This era will end, and when it does, the intergalactic void, the subject of this entire story, will have won. Not by destroying the galaxies, by separating them so completely that they cease to exist for each other. This is the final dimension of the space between galaxies. It is not just far. It is not just empty. It is growing. The silence between the islands is deepening, and the deepening is permanent. What should you take from all of this? Not despair. The facts are stark, but they are not a judgment. The universe is not hostile. It is indifferent. It was not designed to be crossed. It was not built with travelers in mind. The emptiness between galaxies is not a barrier placed to keep us isolated. It is simply the way the cosmos is constructed. Voids are the default. Matter is the anomaly. Galaxies are statistical fluctuations in a field of near nothing, bright wrinkles on a fabric that is overwhelmingly smooth and dark. But there is something in the reckoning that matters. Something that changes how you see the night sky once you carry this knowledge with you. When you look up and see the faint smudge of Andromeda on a clear evening, you're not looking at a nearby object. You're looking across a chasm of 2.5 million light-years of intergalactic void, 1,000,000 times emptier than the space between the stars you see around it. The photons hitting your retina left that galaxy before your species existed. They crust a void that contains almost nothing. A ghost plasma of scattered protons so thin it took our best instruments decades to detect. And they arrived here, tonight, carrying an image of an island so remote that no signal you send in return will arrive there for another 2.5 million years. That galaxy is the closest large one. The rest are further. Most are incomprehensibly further. And between them all, in every direction, the intergalactic void stretches on. Silent, structureless, growing. The space between galaxies is worse than you think, not because the numbers are big, but because the numbers describe a cosmos that is built around absence. The galaxies are not the story. The void is the story. The galaxies are just the bright margins on a page that is almost entirely blank. If the universe were a library, the galaxies would be the ink, and the ink would cover a fraction of 1% of the pages. The rest, every shelf, every volume, every page from cover to cover, would be blank, white, empty, not waiting to be written on. Simply empty by design, by physics, by the way gravity and expansion conspire to arrange matter into thin threads and leave the rest as void. That is what you are looking at when you look at the night sky. Not a crowded cosmos, not a universe full of galaxies, a universe full of nothing, with galaxies sprinkled so sparsely across it that the dominant experience of the cosmos, the experience that any random point in space would deliver, is darkness, silence, the faintest possible plasma, and the nearest island of light, millions of light years away, invisible without instruments, and unreachable without magic. The photographs will keep lying. The maps will keep compressing. The language will keep saying nearby and local and cluster, and people will keep picturing a universe that is cozier than the one that actually exists. But now you know. The space between galaxies is not a gap. It is the main body of the universe. It is where most of the volume is. It is where most of the baryonic matter hides, spread so thin it barely qualifies as substance. And it separates every galaxy from every other galaxy by distances so profound that even the word distance starts to fail. Galaxies are not cities in a country. They are not towns along a road. They are not houses in a neighborhood. They are fires, small and bright, burning on islands scattered across an ocean that has no far shore. The ocean is not water. It is nothing. And it goes on, in every direction, for as far as the universe extends. The most unsettling truth is not that the ocean is wide. It is that the ocean is almost everything. The fires are almost nothing. And the distance between them is not a problem to be solved. It is the structure of reality itself. You are sitting on one of those islands right now. Look up tonight. Find that faint smudge in the constellation Andromeda, and know that between you and it, there is a void so deep, so empty and so vast that even light, the fastest thing in existence, needs 2.5 million years to cross it. And that void is the smallest one your galaxy faces. In every other direction, the darkness goes further. The space between galaxies is worse than you think. Not because it is far, because it is almost everything there is.